Was it a quiz?
Okay, let's go ahead and start. Just a couple of administrative things. A reminder that normally homework 2 would be due today, and in fact homework 2 says it's due today, but as I announced earlier and on the course webpage, it's actually due tomorrow. If you've already turned it in, you still have a day. Just if you turn in, you want to keep working and turn in something tomorrow, just to make sure to write very clearly, grade this one on the one you turn in last, so that we know not to waste our time on earlier stuff. Problem 4 on the current homework. We realized that this problem is actually a bit more accessible if you use some of the ideas that you'll need for homework 3. So we just moved it to homework 3, hoping that then we'll be able to get more submissions. So unless of course you've already turned it in, don't turn in problem 4 with the current homework, wait a week, let it stew, otherwise we're likely to misplace things. Homework 3 is the last homework before on the material that's going to be covered on midterm 1. The homework's going to be due on Tuesday, and the following Thursday is the midterm. It's an evening exam. We have 2 rooms with a total of 200 chairs, so there'll be plenty of space for people to spread out. And following university rules, whenever we have an evening exam, we have to cancel a corresponding number of contact minutes. So what this means is that there is no lecture on Thursday, and there will be no labs that Wednesday. Okay, so no section on Wednesday, no lecture on Thursday. However, completely informally, the TAs will be in the section rooms as usual on Wednesday at the usual times to be, in case you have questions that you want answered about possible material on the midterm. And similarly, just by coincidence, I will be in this room Thursday from 12:30 to 1:45, just because I got nothing better to do, in case you have questions. Right? I can't require any of you to show up, but I will be here. The recording, the video recording is completely automated, so it's actually less work to go ahead and record whatever we happen to talk about in the room on Thursday. Please feel free to come to section on Wednesday and lectures on Thursday with possible questions, either questions that you might have mined from earlier exams, such as the one we will post from last semester, or a couple that we'll post from earlier versions of 373, or just, in general questions about the course material that we've seen so far. Starting this Thursday, we will switch gears and start talking about algorithms, but the material that we'll cover is hopefully all review, at least at the beginning. It's just, let me remind you how recursion works. And the first homework on that material will be released after the midterm, so that at least in terms of the stuff that you're working on and thinking about, you can focus on the midterm until the midterm is over. There'll be a sign-up page on the main course webpage if you need to sign up for a conflict. That'll hopefully be up in the next day or so. So if you need a conflict, watch out for that. So far, only a couple of students have sent me email about needing a conflict. If it's just a couple of you, then it's pretty easy. We can figure out one time. Okay? Any other questions? Yes?
So you said you're going to post the sample midterm from?
I'm going to post last semester's midterm, and I will try to get a sample midterm put together, although basically this means, I'll write the exam with twice as many questions and then decide these aren't good exam questions, and that will be the practice midterm. I haven't, as I said, this is really my first time teaching this material, so I can't promise that the practice midterm will actually be reflective of a real exam, because I've never written a real exam for this. You all are guinea pigs. As usual, I will aim for an exam that, if you really know what you're doing, you can finish in less than an hour. I always say that, and it never actually happens. The word that you want to keep in your head is curve. Okay? Nevertheless, we don't want an exam that is completely unfair. What I generally would like to aim for is a median score of somewhere around 60 to 70%. That is gives us, the most signal. We get enough of a spread that we can actually distinguish who's doing really well from who's doing kind of well, from who's doing sort of well, from who's doing not really that well, without being totally discouraging. Someone asked on Piazza, if we only get a 3 out of 4 on every homework, does that mean we have a C homework average? No. A 3 means, yeah, this is pretty good. The C doesn't. So don't think that we're on some sort of 90s or an A, 80s or a B scale. That never made sense to me. The material is really, really hard. Getting 80% of it is actually doing really, really well. Okay, other administrative questions? All right, so on Thursday we started talking about non-determinism. And so, we had things called NFAs, which, without going into the formal definition again, a good example of an NFA is this object, right? It looks like a state machine, but it's not a deterministic finite state machine, because in some states, I don't have a unique choice about how to transition when I see a character. So if I'm in the start state on the left and I see a 0, I could either stay put or I could go to the top. So this is what non-determinism means. It means the behavior of the machine is not determined uniquely unambiguously by the input. I have choices that I can make. And sometimes, for example, at the top state, I may not have any options at all. So if I'm in the top state and I see a 1, there's nothing to do. The machine simply crashes. It ceases to exist. The universe explodes. That option is retconned out of existence. Just pretend it didn't happen that way. Okay, so sometimes you have multiple options, sometimes you have none. Sometimes you have 1, if you're in the top state and you read a 0, you can't do anything except go to the right. So a DFA is just an NFA where for every state there is exactly 1 arrow with each symbol. An NFA allows you any number of arrows with the same symbol on it. Okay? So we've so far seen 3 different models of languages, right? So there was this generative model called regular expressions. There was this, I guess you might call it, AI people would call this a discriminative model, called DFAs. It can discriminate between languages that are in strings that are in the language and strings that aren't. It can decide whether a given string is in the language. You really should think of it as a machine. And I don't know what the correct adjective form here is. And you've got NFAs, which are not really machines. They're not really algorithms in the same sense as a DFA is, because you've got these choices that you can make, and you don't have directions about which choice to make. You have lots of different choices, and only in retrospect do you get to see which of these choices were correct. But you can use an NFA to verify or to prove that a given string is in a language. So I can verify that the string 1110011 is in whatever language this thing is describing by saying, 11110011. Hey, look, I ended up in the accept state. It's possible to end up in the accept state. I could have also said 1110010. I cease to exist. Those sets of choices weren't right. So if I want to verify that a string is in a particular language, I can describe an NFA for it, and then for any particular string, I can tell you which choices to make. So what I want to do today, finally, is I want to try to convince you that the languages that you can describe with regular expressions are exactly the same as the languages that you can describe with DFAs, which are exactly the same as the languages that you can describe with NFAs. Okay, so this is sometimes referred to as Claney's theorem. Claney was the guy who came up with regular expressions in the first place, and there were other people who came up with DFAs, but then Claney realized and published a paper that said, hey, look, these are actually exactly the same languages, and we call those languages regular. Okay, regular languages can be described by regular expressions. They're accepted by a DFA, and each one is accepted by an NFA. And moreover, I can go back and forth between these representations mechanically. Given a regular expression, I can compute with an algorithm a corresponding DFA or corresponding NFA. Given an NFA, I can compute a corresponding DFA. Okay? So that's what I want to try to show you today. I'm going to be necessarily a little bit loose with the details. I'm hoping that the details will eventually end up in the notes. Most of them are already there, but there are, here, look, there are notes. But there's some gaps, like which I still haven't filled in. I'm going to try to get to those long before the end of the week so that you can apply them in the homework. Okay, so but before I start proving these equivalences, it's actually a little bit simpler if I add something to the NFA model that's fairly common and intuitive, and many of you have seen this already in other contexts. This is the notion of an epsilon transition. Okay. So the idea behind an epsilon transition is I want to be able to change my state without actually consuming any input at all. Okay. So here is another NFA, this time with epsilon transitions. It's clearly going to be equivalent to the NFA that we saw earlier. Okay. So here is a slightly different flavor of NFA. Okay, so the idea is that I'm initially going to start, over here in the start state. And then I can decide, before I read any inputs, I can decide if I want to follow one of the arrows labeled with epsilon, say I go down here. And then after I'm done following epsilon arrows, I read a character from the input and follow one of the outgoing arrows with that symbol on it. Right? So if I made this decision to follow the epsilon arrow down, and then I read a 1, I'm happy because I actually have somewhere to go. Right? And now I'm going to change. I'm going to change the language here slightly. Well, if I added an epsilon arrow, let me leave it alone. Okay. So if I'm in this bottom middle state, there are no epsilon edges going out, so I don't have any options except to read a symbol. And then if I read a 1, I can transition to the right, and if I read a 0, I cease to exist. Okay. So the idea now is that an NFA with epsilon transitions accepts a string W if there is a sequence of transitions that, say, starts here at the start symbol, ends at some symbol in the accept state. Each of these symbols is, each of these transitions is labeled with something where this something is either a symbol in my alphabet or an epsilon. And the string you get when you concatenate all these things together is the input string W. Okay? So if there is a sequence of transitions that has the right label, meaning if you concatenate the labels on the individual transitions, you get a string that's equal to the input string, and you start at the source and you end at some accepting state. Right? So, for example, in this particular input, I might call this A, B, C, and we'll call that X. Okay. So that sequence of transitions up at the top is a proof that this NFA accepts the string 0, 0, 0, 1. Okay? So, all right, 0, 0, 0, 1. There's a formal definition that involves, changing the signature of the transition function, changing the definition of the extended transition function delta star. I think the picture is hopefully, clear enough. Right? So any confusion about what an epsilon transition actually means? Okay. Again, this is still non-determinism. That is not the only sequence of transitions that would accept that string. For example, I could have taken the epsilon transition up to A at the beginning and then gone from B to C with the first two zeros and then eaten up the third zero over in the accept state X. So there isn't necessarily only one way to accept the string. It's enough that there is at least one. Okay, and again, you can hopefully convince yourself that if the input string just alternates between zeros and ones, 0, 1, 0, 1, 0, 1, 0, 1, 0, that no matter whether you take epsilon transitions or not, there's no way to get to the final state. Okay, there's no way to accept. All right, so this is great. It looks like I've made my machine somehow more powerful. Yes?
Can you make every NFA?
Good question. As I was saying, it looks like I've made the machine model more powerful, but I haven't. So, in fact, yes, you can get rid of all epsilon transitions. So, if I allow epsilon transitions and you don't use them, that's perfectly cool. So, an NFA without epsilons is also an NFA that could have epsilons but decided not to. Okay? Just like a DFA is also an NFA that decided to be deterministic. Okay? An NFA really is a DFA really is a special case of an NFA. An NFA without epsilon transitions really is a special case of an NFA with epsilon transitions. So here's how you get rid of them. Okay, here's how you get rid of epsilon transitions. So I'm going to define the epsilon reach of a state. I'll call the state P. This is P itself, or any state Q such that there's an epsilon transition from R to Q for some R in the epsilon reach of P. Okay, so this is a recursive definition, but intuitively what it means is there is a sequence of epsilon transitions from P to Q. Okay? Right, so if I can find a sequence of epsilon transitions through any number of intermediate states, starting at P and ending at Q, then Q is in the epsilon reach of P. Right, the epsilon reach is intuitively, if you find yourself in state P, then you get to decide for free that I'd rather be in one of these other states. Right, and the epsilon reach is the states that you can just freely decide to move to. Right. Now I do want to be I do want to emphasize one subtlety here. Q is in the epsilon reach of P if I have an NFA that includes this path like this, but P is not in the epsilon reach of Q. This is not a symmetric relationship. Okay? Sometimes it's a symmetric relationship. If I added another epsilon back from Q back to P, then all of these states would be in the epsilon reaches of each other. But in general, I'm not describing an equivalence relation. I'm just describing from here, I can go to there for free. Okay? All right, so epsilon reach. So, now let's suppose I'm given an NFA that has epsilon transitions. Right? I'll call this machine M. This is has an alphabet, a set of states, a starting state, accepting state, and this weird transition function that takes a state and either a symbol or a marker epsilon and goes to some set of states. Okay, that's the formal signature for an NFA with epsilon transitions. The difference being that I allow transitioning on epsilon. So I can construct an equivalent NFA without epsilon transitions, I'll call that M prime, by saying, well, I'm going to have exactly the same states, Q. I'm going to have exactly the same start state, S. My accept state for my new NFA without epsilon transitions is this going to be all states Q such that the epsilon reach of Q includes some state in A. So the idea being, if I can get to a state where I can freely go just change to an accepting state, I might as well say that I'm already in an accepting state. Yes? All right, so let's suppose I'm in a machine where I end my execution at this state here on the left side of the room, but there's an epsilon transition over here to the right side of the room, and over here on the right side of the room is an accepting state. Well, I can go from here to there for free, and that's an accepting state. So I might as well say that this is also an accepting state. That's all that formalism says. If I can reach an accepting state through epsilons, I might as well say I'm already accepting. And then the last thing is I need to define what to do when I'm in a state Q and I read a symbol. And the intuition is first, before I decide how to consume the character A, first I'm going to try to execute as many epsilon transitions as I want. Right? So this is going to be the union over all states P in the epsilon reach of Q of, well, the old transition function starting at P. Okay, so this just says take as many free transitions as you want. The epsilon reach is the things you can end up in, and then from there you have choices about how to branch on the character A. Okay? And that's it. And I guess I should say, just to be pedantic, no, you can't transition on epsilon in the new machine. Okay? So any remaining epsilon transitions just get thrown on the floor. Right? So to show you what this means, let me show you the example. All right, here's the machine that I just showed you. All right, so I'm going to have a new machine that's going to have exactly the same states. Okay, and it's going to have the same start state S. Now, the state on the far right is an accepting state in the old machine, and the states next to it on the right can get to an accept state in one step. So in my new machine, I'm going to have 3 accepting states. right? The original accept state X, the rightmost state C, which can reach X, and the state below C, which can reach X. Okay? And so all I have left is to figure out what I can transition to. Okay, so let me start by looking at transitions from on symbol 0. Now some of these I don't have any choice. So for example, from this state B here at the top, if I read a 0, I can only go to state C. Right? There are no epsilons out of B, there are no choices out of B, so I don't have anything I can do. Similarly with A, I have to go here on a 0. Right? So some of these things are easy. The more difficult one is, so suppose I'm in state S, and I see a 0, where can I go? Well, I can either stay put, because I didn't take any epsilon transitions, or I can follow an epsilon up to state A, and then follow the 0 over to state B. Right. Similarly, if I'm in state C and I get a 0, well, I can either not follow the epsilon and then die, nothing happens, or I can choose to follow the epsilon and then I'll end up in state X. Right. So if I follow these rules all the way through, I get an NFA that looks like this. Now you'll notice something about this NFA. It's got more states than it needs. Okay, fine, whatever. Right? This state down here on the bottom left, I can never get to it. There are no incoming transitions. The epsilon arrow that came into it vanished when I did this transformation. Similarly, once I end up in one of the accept states on the right, I'm always going to be in an accept state. So those 3 states on the right are actually all equivalent. All right. So I can, without too much difficulty, actually, I can shrink this this NFA down to, well, this one. Right, these are exactly the same. And again, there's an algorithm to do this, which I don't want to tell you about because I only have so much time. Right. Yes?
So you said that, so in the Epsilon transition diagram on state C, choice whether or not to Epsilon transition to the second state.
Yes.
But when you transform that into the non-Epsilon thing, you lose that, like...
Okay, so let's be careful about where this arrow here, this arrow out of state C comes from. Okay? So in the original machine at the top, when I'm in state C, I have a choice. I can either follow the epsilon arrow or not. If I don't follow the epsilon arrow, and then I decide to read a 0, I explode. I cease to exist. If I do follow the epsilon arrow, then I end up at state X, and from there, if I read a 0, I stay in state X. And that's where this arrow comes from. This arrow actually corresponds to this pair of transitions.
But then in the bottom diagram, you don't have the choice to explode.
That's right. That's right. In the bottom diagram, I used to have a choice, and now I don't.
But doesn't that change the meaning of...
Well, no. I mean, if you want, you could chase this through formally, but if I'm in the old machine and I'm in state C and I read a 0, where can I end up, really? I have a choice to either go to the accept state or to kill myself. I'm going to choose the former. Okay? Then I explode, both here and here.
Like, what I was saying was, like, in the bottom one, like, you don't have the choice to, like, explode or kill yourself. You have to go to 0, or you have to...
No. If I'm in state C and I read a 1, what do? The transition function tells me I cease to exist.
No, because you go to X.
No, if I am in state C and I read a 1, there is no arrow leaving state C that has a 1 on it.
On the top one.
Oh, on the top one. Oh, you're right. I'm misread. Okay. There we go. That's what, okay. Sorry. Yes, thank you. My mistake. Okay, so C and you read a 1, then you read an epsilon. You have to read the epsilon and then you spin. Okay, good. Good, okay. All right, so any, I can throw in epsilons, I can take out epsilons. It doesn't change which languages I can accept. Yes? I could. No, it wouldn't change anything. But what I want to emphasize is the transformation from this machine at the top to this machine at the bottom is completely mechanical. Once I've done that mechanical transformation, I might then be able to notice, hey, I can collapse some things, or I can throw some things out. But that's not part of the mechanical transformation. Okay. So what this means now is that when I'm reasoning about NFAs, the choice of whether or not to include epsilon transitions is entirely one of convenience. If I'm trying to construct an NFA, generally allowing epsilons gives me a bit more flexibility, and so I will generally want to include them. But if I'm thinking about an algorithm that's given an NFA as input, then by leaving out the epsilon transitions, I remove some flexibility that the algorithm would otherwise have to deal with. And so in those circumstances, generally I want to assume that NFAs don't have epsilon transitions. So if I start with an NFA and I know nothing else, I should assume there are no epsilons. But if I'm trying to build an NFA, it's okay to use epsilons, because I can mechanically go back and forth. Okay? So in particular, on the homework, if it asks you to build an NFA, throw all the epsilons in you want, as long as it's right. Okay. Good. So now the proof of Kleini's theorem that all these three different descriptions of languages are actually equivalent is now essentially going to go like this. Okay. Given an object somewhere in this sequence, I'm going to describe an algorithm to follow one of these arrows. Now, one of these arrows you already know how to do. Which one? Let me say that, you may be right, but let me say that a little bit more carefully. One of these transitions you already know how to do, and moreover, you can describe the algorithm completely with one word. At 2 words, okay. How do you transform a DFA into an NFA with epsilons? Do nothing. Okay? This arrow is completely trivial. Right? A DFA is a directed graph where every node has exactly one outgoing arrow with every symbol on it, and no epsilons. An NFA is a directed graph where the outgoing arrow, every arrow is labeled with a symbol or an epsilon. So I just said, okay, I'm allowed to use more than one outgoing arrow with a given symbol on it, but I just don't want to. I'm allowed to use epsilons, but I just don't want to. I'm allowed not to have an arrow with a symbol 0 leading out of a state. I'm just not going to do that. Right? That's the entire transformation from DFAs to NFAs, including the epsilon transitions. Okay? All right. So I have 3 steps left to go, and I'm going to do them in this order, which is strangely not the order that I wrote the numbers down, but I am in fact going to do them in this order. Okay? So let's start with going from NFAs to DFAs. Is it for me? Okay. Okay, so as I just said, because I know that I can get rid of any epsilon transitions in the NFA, I'm just going to start out assuming that there are none. Right, initially. I'll back up and show you exactly how to deal with epsilons in a second. But for now, let's suppose there are no epsilons. And I'm going to start actually by just showing you an example. So this is the same example that we've seen many times. Okay. Right, so remember, in an NFA, you have this transition that takes a state and a symbol, and it gives you a set of states. Right? Now, what I'd like to be able to do is describe, if I want to think about what an equivalent DFA might do, well, I want to think now of the NFA in the notion of executing a bunch of parallel threads. Okay, so I might start out like this, and then I read a 0, and then this will transition, and it will stay put. And then I'll read a 1, this will die, this will transition and stay put. Then I'll read a 0, this will die, this will transition and stay put. Then I'll read another 0, this will transition and stay put. Then I'll read a 1, this will move here, this will die, this will transition and stay put. Okay. If I'm imagining this sort of synchronous parallel version of executing an NFA, how do I describe the configuration that the NFA is in? How do I describe the state of the NFA? Your tuple is close, but tuple, there's an ordering that doesn't matter here. Right, so the state of the NFA, the state in which the NFA finds itself, is completely described by me telling you which of those little circles has a token on it. Okay? So the states of my DFA, which are exactly the subsets of the states of my NFA. Okay? I am currently, let me again label these things. I'll call this S, A, B, X. I am currently in state SAX. Because in one of my parallel threads, I'm in state S. In another parallel thread, I'm in state A. In a third parallel universe, I'm in state X. Okay? So given that, what is the starting configuration of my NFA? So pretend I'm a typewriter. What do I put here? What symbols do I put here? Open brace, S, close brace. My current configuration is the state, is the set containing S. The current set of states that could possibly be active is of size 1. It contains a single state, S. Right? This is mostly confusing because now I'm using the word state to mean two different things. But when I say, my deterministic state is a set of non-deterministic states. And the start deterministic state is the set containing the S, the start state of the NFA. Okay. What are my accepting configurations? So, this is one of them. How do I describe the set of configurations of the NFA that I should be considering to be accepting? Well, now keep in mind, what is A prime? What type is A prime? A prime is a subset of Q prime. Q prime is a set of sets of states. So A prime is a set of sets of states of the original NFA. All right, so it's going to be a set, and it's going to contain subsets of Q such that within that subset, I have at least one accepting state. Okay? In other words, A prime is all the different ways that I can put tokens down on the picture such that there is at least one token on the accept state. In fact, there is a token on the accept state. I guess that's the right way to say that. Okay, so P tells me which circles in that picture to put tokens on, and P intersect A is non-empty, says, well, there's a token on one of the accept states. Okay? And then finally, I need a transition function, right? Well, the inputs to the transition function, this is a set of states in M, right? Here's a DFA is called M. This is just the union over all states in that set of the old transition function from P, starting at A. Okay? So if I want to know if my tokens happen to be here, let's say my tokens happen to be here, and I read a 0, what should I do? Well, all the possible places that tokens can move around, what I'm going to do is, for each token, I figure out all the places where that token can go. So this token at the bottom, when I read a 0, the only thing it can do is cease to exist. This token at the top, the only thing it can do is move to the right. And this token on the left can move up and stay put. Okay, so if I'm in this configuration and I read a 0, I end up in that configuration. Right? This is what these symbols mean. Okay? All right. Now, I'm going to take this away because you can watch the video later and you can see it in the notes. But I want to show you how you would actually do this in practice if you were actually asked to execute this algorithm. And I'm actually going to do it on the more complicated one that has epsilons. Okay. All right, so I'm going to start A, B, C, D, E, F, X, 0, 1, epsilon, epsilon, 0, 0, 1, 1, nothing, nothing, anything. Okay? So you can chase through the definition, through the algorithms that I just showed you to first, let's get rid of the epsilon transitions, and then let's produce this DFA using the subset definitions. And you'll get something reasonable. In this particular case, you'll get a DFA that has 16 states, or no, sorry, 256 states, 2 to the 8, because I have 8 states in my original NFA. But I'm going to get something a little bit more compact by building the DFA incrementally. I'm just going to show you this by example, because I think the example is good enough. Okay? So the idea is, when I'm building my equivalent DFA, one of the things I don't want to do is I don't want to bother with states that I can't reach from the starting configuration. So the way that I'm going to do that is essentially I'm going to run breadth first search. I'm going to start in the starting configuration, figure out every other configuration I can get to, and then for each of those, figure out every other configuration I can get to from there, and from those, figure out every configuration I can get to from there, just making sure not to ever duplicate anything, not to ever reconsider a configuration that I've already figured out. Okay, so I'm going to start in state S. Now that, I'm deliberately omitting the braces when I write this down, but what that really means is the set containing S. This is my DFA state, not my NFA state. Now I've got 3 columns here, one labeled epsilon and the other 2 labeled with the symbols of my alphabet. And what I'm going to do is first I'm going to figure out what I can get to only by following epsilon transitions. And then from there I'll figure out what I can get to with a 0, and from there I'll figure out what I can get to from a 1. So if I'm in, there they are. If I'm in state S, and I can follow an epsilon transition to either A or to D. So I am sad. Okay. Now, given that I'm in one of these 3 states, where can I get to by reading a 0? Well, if I'm in state S and I read a 0, I end up back in state S. If I'm in state A and I read a 0, I end up in state B. If I'm in state D and I see a 0, I cease to exist. Similarly, if I'm in one of these 3 states, SAD, and I read a 1, I'm going to end up in S or E. Now at this point, these are configurations I haven't processed before. So I'm going to write them down in the left column. And now, as long as I've got something that I haven't processed yet in the left column, I'll process it. So suppose I'm in state SB, and now what can I get to from there following any number of epsilons? Well, I can stay at S, or I can follow an epsilon out here to A, or I can follow an epsilon down here to D, or I can stay at B. B doesn't have any outgoing epsilons. And from there, what can I get to by reading a 0? Well, from S, I can stay at S. From A, I can go to B. From B, I can go to C. And from D, I cease to exist. All right. What can I get to by reading a 1? From S, I can stay at S. From A, I cease to exist. From B, I cease to exist. And from D, I can go to E. So I get to write one more symbol down. Okay? Now, let me go through this a little bit more quickly. S, A, D, E. This can go to SB or S. SEF. All right, from SBC with an epsilon, I can stay at S, or I can go to A, or I can go to D. From B, I can't do anything. From C, B, I can stay put. C, X. All right, now notice, at this point, I've discovered that following epsilon transitions, I can get to an accepting state. From SBC, I can somehow reach an accepting configuration. So that means SBC is itself going to be an accepting state. Okay. All right, fine. What do I get from a 0? From S, I can go to S. From A, I can go to B. From, I think that might be for me. From C, I can't do anything. From D, I can't do anything. From X, I can go to X. So S, B, C, X goes down here. And the other way, with the 1, I can go to S. From A, I explode. From D, I go to E. From B, I explode. From C, I explode. And from X, I go to X. Okay? And so on. All right? At this point, without going through the rest of the details, I can actually reveal that everything else, it's not too hard to guess, everything else that I'm going to consider is going to be an accepting state. And all transitions out of those accepting states are going to lead to other accepting states. Right? Everything is either itself a subset that contains the letter X, or I can reach X with an epsilon transition. And once I can reach X, then every transition is going to stay at X. So all of these are really just equivalent accepting states. And so I'm going to end up with the following. So if I can read a 0 and go there, or 1 and go there, 1, 0, 1, 0. Right? And I'm going to end up with a DFA that looks like that thing on the right. Okay? Where each of these DFA states correspond to a subset of the states in the NFA. Now, at the point where I said, okay, I'm going to stop grinding through here and notice, oh, everything down here is going to be an accept state, I've left the sort of algorithmic part of doing this. But, you know, I don't want to go on because it'd just be kind of mechanical and boring. Okay? So the order of events is this. And I just, as long as there's some unprocessed state on the left, I produce a new row, and then every configuration that I see in column 0 or column 1, if I haven't seen it before, I write it down on the left. Yes?
So I understand that SEF is an exception.
Oh.
But why don't we just write a state for SEF that's...
I'm at this point, I'm basically being clever. Right? If I were doing this mechanically, I would say, okay, from SEF, I can get to SADEFX. That's an accepting state, check. And from there, I can get to SEFX with a 1, or to SCX with a 0, and then I start writing more stuff down and grind, grind, grind. Okay, but at this point, I can already see that everything else I'm going to consider is going to have that accept state X in it. So I'm not going to bother. I'm just going to stop. Okay? Good. All right, so this is what is commonly known as the subset construction. And there's two flavors. You know, you can just do it all at once, or you can do it incrementally. All at once just means you just look at the definition and say, well, let me just write all this stuff down. Incrementally tends to give you something significantly smaller. Even if I had ground through this in complete detail, I would have ended up with a DFA that had maybe 10 states, as opposed to 256. Okay. So, good. I can turn any NFA into a DFA, whether or not it has epsilons. Good, so all these finite state machines that describe the same families of languages. How do I fit regular expressions into this? And so first I'm going to describe how to get from a regular expression to an NFA with epsilons, but I'm going to do it with a particular type of NFA which is, I'm going to draw a picture that looks like this. There's one accepting state. Now this is not much of a restriction, because if I take if I have an NFA that has multiple accepting states, I can produce an NFA with one accepting state by just saying, okay, this is now the accepting state, and I put in epsilon transitions, and now these are no longer accepting states. All right, so I can take something that has a bunch of accepting states and transform it into whatever else the rest of it is. Okay, so without loss of generality, from now on, all NFAs have exactly one accepting state, and it's different from the start state. Okay? All right. Now let's recall the definition of a regular language, right? Or regular expression. L is regular if L is empty. Okay, so can somebody describe to me an NFA that has a start state and exactly one accepting state, which is different from the start state, that accepts the empty set? All right, so just to be clear, I need a start state, and I need an accepting state that's different. And what else do I need to add to this NFA? Good, you all got it. This is an NFA. The transition function always returns the empty set, right? How do you transition on a 0? Nah. How do you transition on an epsilon? Nah. You just die. So no matter what the input is, you just die. Except if the input is the empty string, and then you can just stay still. You go, I'm not going to die, I'm not going to die. Oh, I didn't make it. Okay? Great. Another possibility is L is the set containing the empty string. Can anybody tell me what that machine might look like? What do I need to add? Anybody? An epsilon transition. All right? Because now what happens is, if I read anything, I have to follow a real arrow that has a 0 or a real symbol on it. Right? So if I read any symbol at all, I have a choice. I can either stay at S and then explode, because there's nowhere to go when I see a 0. Or I can take the epsilon transition over to T. Yay, it's an accepting state, and then I read a 0 and I explode. Okay? Whereas on the empty string, I can stay put at S, and then, okay, I'm sad, but at least I'm alive. Or I can go over T. Yay, we win, I accept. Okay? Yes?
Well, couldn't then as well reading nothing mean something taken by?
Right, so I may as well assume at this point that S is an accepting state, but I'm not going to, just because I want to maintain this discipline that I could make S an accepting state at this point, and it wouldn't change anything, but I don't have to. So I really want to maintain this discipline that there's one accepting state and it's not S. Okay. So another possibility is L is a language that contains a single word, a single string. Okay. What do I need to add? And just, let's say that W is the string foo, just to be concrete. What do I need to add? Yeah. Well, remember, the transition, I'm supposed to transition on individual characters, but that's essentially it. Okay. I just add a sequence of states, one less than the length of the word, and then I add the individual characters along those transitions. And then if I read anything other than that string, the execution is either going to end in a non-accepting state or it's going to explode along the way. Okay, so these are the base cases. Right now, I also need to consider the recursive cases. Okay, so L is A union B, where A and B are themselves regular languages. And what that means is I have something that accepts A and something that accepts B given to me by the inductive hypothesis. So, and somehow I want to combine these to get an accepting, a DFA that accepts the union of these two things. So what do I need to add? Right, so I add epsilons from the starting state for L to the starting state for this machine and the starting state for that machine. And then I add epsilons going the other way. And then I say, well, actually, those are no longer accepting states anymore. Okay? So I take the two component machines for A and B, and I connect them in parallel. And that gives me an NFA for the union of these two languages. Yeah?
Why are those three not accepting states anymore?
Because I want to insist that the NFA that I build has exactly one accepting state.
Why?
Because I'm assuming that A is accepted by an NFA that has exactly one accepting state, because that's where I'm going to glue the epsilon on. If A had other accepting states, I can't have to reach inside and glue in more epsilons. I could do that, but this just keeps it simpler. Okay? Okay, so that's a union. There's two more cases. How do I build a machine for the concatenation of A and B? Right? Again, I have a machine for A, and I have a machine for B, and I now want to create something with a new start state and an accepting state. What do I do?
Just go through the A machine.
Right, and then make these not be accepting states anymore. So to handle the union, I connected the two machines in parallel. To handle concatenation, I connect the two machines in series. Okay. Now, the one that's actually subtle. Anyone want to guess what I need to glue onto the machine that accepts A in order to get... Yeah, sorry, yes.
Why do you need to add the accepting state?
What? Sorry?
In A concat B, why do you need the accepting to add another accepting state?
Habit. Why not? So I didn't actually need to introduce a new S. I could have started at the start state for A. I didn't actually need to introduce a new T. I could have ended at the accept state for B. But I'd already drawn S and T on the picture and said, how do you connect these up? So, okay, connected them up. This is more states than I need, but again, why do I don't care if I have more states than I need, because there's an algorithm that will take the extra states away. All right. Okay, so I have this machine A. I have the start state for that machine on the left and the accept state for that machine on the right. And now I want to build a new machine with start state S and accept state T that accepts A star. Yeah.
You can put an Epsilon transition.
Perfect. So I have a choice to do nothing. Right? This is the definition of A star. I could do nothing, so I need to be able to jump directly from S to T. Or I could go through A, and then, if I want, start over. Okay? Now, in this particular case, there is actually a subtlety here. Why didn't I just do this? Why didn't I just do that? Right? There's actually a reason why I introduced a new steps S and T in this case. And the reason, if let me actually show you a state machine for a language A. Okay? This machine accepts all strings of the form 0 star 1. Now, if I'd added an epsilon here and an epsilon there, that does not accept the language 0 star 1 star. Right? For example, it accepts the string 1, which it shouldn't. Right? Every language that, if I'm trying to build something for this language, every string in this language is either empty or it starts with a 1. Or, sorry. 1 star 0, sorry. Every string in this language is either empty or it ends with a 0. But that NFA, with the unlabeled arrows or epsilons, accepts the string 1 epsilon. Right, so I need to be careful not to actually involve the actual start state for machine A. I need to pull back and have an artificial start state. Otherwise, I might get something incorrect. Okay? And that's it. That is how you build an NFA out of a regular expression. If the top level operation in the regular expression is a concatenation, you connect in series. If it's a plus, you connect in parallel. If it's a star, you put this ring around it. And the base cases are the empty set or a single word. Okay? So that's NFA to regular expression. Which leaves me with, this is an algorithm by somebody named Thompson, which leaves me with step 3, which, given the amount of time I have left, I'm going to have to wait until Thursday. So are there any other questions on either the subset construction or this recursive construction of NFAs from regular expressions?
So the choice of one accepting...
Right, so I basically constrained what the construction is going to produce so that I have exactly one accepting state, so that in the induction hypothesis, I can assume that my component machines each have exactly one accepting state. All right, so I'm proving something, I'm imposing some additional structure so that I can make a stronger induction hypothesis. Okay. All right, thank you. See you on Thursday.